Hello everyone, and welcome to another Leetcode video. Today we're looking at the coin change problem, how to solve it with tabulation. If you have not watched the previous memoization video, I highly recommend you go and watch that first, since this is a direct follow-up to that video. So the question reads that we are given an integer array coins representing coins, different denominations, and an integer amount representing the total amount of money we have to make. So we want to return the fewest number of coins that we need to make that amount, and if we cannot make that amount, we return a -1. And we have an infinite number of each coin, so we can use as many as we like. So an example is that we have the coins 1, 2, and 5, and our amount is 11, and we can make this with 3 coins, being 5, 5, and 1. So we're going to look a bit closer at this example, but before we do, I just want to discuss why we would want to use tabulation. So in the previous video, I kind of outlined this kind of sequence to get into a dynamic programming solution. So first we find the brute force approach. This usually involves using recursion. After that, we want to optimize by using memoization. So we're still going to use recursion, but we're going to cache intermediate values so that we can reuse them. And then finally, and this is usually considered the optimal step in dynamic programming, is the tabulation approach, which is a bottom-up approach, which does not use recursion, but instead is solved iteratively. So why would we want to use tabulation? In most cases, just getting to the memoization solution will be perfectly adequate. For most questions on Leetcode, this will be totally fine. For most interview situations, this will be totally fine as well, unless they specifically ask for tabulation. But there are a few reasons why you might want to default to one or the other. So for tabulation, it might just make more sense to you. I know for some people, recursion is just tricky, no matter how much they study it. So if tabulation makes more sense for you, you could always go right to this option rather than working through the memoization first, then converting it. Also, in Python, there is a pretty low overflow limit. So if we use recursion, there's a good chance that in subproblems, we will run into a stack overflow, even though our solution technically is correct. For most Leetcode problems, this won't be a huge issue, but if you're doing like code forces or @coder or code chef, something like that, you'll definitely run into this. There have been situations where I've had to take my memoization approach and convert it to tabulation just to solve the problem. And even on Leetcode, some very hard questions can only be solved with tabulation, but this is a pretty rare case. There was a contest recently where there was a DP problem that needed to also use prefix sum along with DP, and this is really only possible by using an array with tabulation. But this was a question that only had like 1% solve rate, so this is like a very rare edge case, and I think for most questions on Leetcode, this shouldn't really be an issue. So the way we can solve this with tabulation is by using an array. And we're going to start with an array that is the size of our amount plus 1. So you'll see that our amount is 7. We have 1, 2, 3, 4, 5, 6, 7, 8 elements in our array. And all of these elements are going to start as infinity or just some very large value. And the first thing we're going to do is we're going to take this value 0 and we're going to make this 0. And why do we do this? Well, this kind of represents the case where we are having to make an amount of 0. So each of these numbers represents an amount, and the value will be the minimum number of coins it takes to make that amount. So logically, it makes sense to say, if we don't have to make any amount, we can just call this 0. It takes 0 coins to make an amount of 0. So this is kind of our base case and our starting point for tabulation. So then, how do we actually solve this? Well, we'll start at 0. Let's now go to 1. And what do we do here? Well, we could say, let's look at our coins. For each position we're at in the array, we're going to go through all of our coins, and we're starting at 1. So we'll say, okay, we're at 1. Let's look at our coin of 1. So if I have 1, let's find other values that previously we solved for that I can add coins to. So what does that look like? So for example, if we're at 1 and we have a coin of 1, this means that previously, if we look at this value here, it means that we could take whatever value we see in this spot, right? And we can just add 1 to it. And why can we do this? Well, because we know the number of coins it took to solve that previous problem, And now we can add this 1 coin to it. So our value would become this plus that 1, right? So now our 1, we could say, okay, well, we've seen that we can make this with 1 coin, but let's also check the other ones. So we can do the same thing for 2. So we're still at 1 here. We say, okay, let's check out our 2 coins. So if you do 1 minus 2, that gives us -1. But this doesn't make sense, right? So -1 is not really a valid amount that we can have. All our amounts here are positive. So if we ever see a negative number, if whatever value we're at minus the coin is negative, we just don't even consider this case. So 2 and 3 in this case are not valid, so we can just continue past, basically. So after this, we would go to our next. So we'd go to spot 2. So we do the same process. We would check all of our coins. So we would say 2 minus 1, we check this first coin, equals 1. So we can look at this spot here and say, okay, so to get to 1, I had 1 coin here, but then I can take this coin here and just add that coin to get a value for 2. So I can now say, I'm taking this previous value and adding 1. So we can see, all right, we found a way to make 2 using 2 coins. So then we'll go to the next one, right? We'll say, okay, so I'm at 2. Our next coin is 2. So we can do 2 minus 2 equals 0. So what's this tell us? Well, we can use this 2 coin here and add it to whatever value we had here. So we'll go to spot 0. We'll say, okay, well, the minimum amount of coins to make this was 0, but we can add this 1 2 coin to it. So this will give us 1 overall. But you see we already have a value here, but this 1 is less than this 2, right? So we always want to update this with the minimum value. So we now see that the minimum number of coins here to make this is 1. What the decision we're going to make at each point is can boil down to the following. So we're going to take the minimum of whatever the answer is that we're looking at, right? So say we're looking at this spot 2, and we have a 2 here, right? So this should be our 2. Or we want to look at the spot I minus our current coin, right? So it would be the index of 2, and say we're looking at this 2 coin, so this would equal 0 plus 1, right? So basically what we're saying is whatever previous answer that we've already found, let's compare that to this new answer that we're going to find. And this new answer, we're just going to find in the same exact way. We're basically going to simulate adding that coin in, which is where our plus 1 comes from. So we're going to look at a previous problem that we have found. So in this case, we're looking at 0, and we're going to say, I know the answer here, and I can add this 1 coin in. So I'm just going to compare the answer I found to this new answer, and then that will be the answer I'm going to update my value with. Then at the end, what we're going to do is we're just going to, after we solve all these problems, just take our DP array and take the amount value. Because remember, this is what we're looking for, right? So after we've solved all these problems, we can just take this value out of the array and we can return that. So what is our time complexity here? So we have to go through every amount value, right? So we can call this n. N is our amount. And remember, for each amount, we have to go through all the coins. So we can call our coins s. So it's pretty simple. For every element in the array, we have to go through all the coins. So our time complexity is O of n times s. And our space is also pretty simple. We're just keeping track of one element for all of the amounts. So our space complexity is just n as well. So hopefully this made sense. Let's hop over to the code and see exactly how we can solve this. So the first thing we do is set up that DP array. So like we said before, this is going to be infinity at every spot, but we're going to add in our starting case of 0. So for 0 coins, the minimum amount of coins we need is 0. This is our base case and where we're going to start. So then we're going to go through every amount, and then for every amount, go through each coin. So remember, we were doing for every element, going through each coin. So this is the case where the value we're looking for is a positive index. So remember, if it's ever negative, say we're on I of 1, but the coin is 3, then this value would be less than 0. And this doesn't actually make sense to check for this. So we're just going to do a check and only actually do this computation for positive amount values. So then what we're going to do is we're going to update the answer for this problem. We're going to say the answer is the minimum of whatever I found so far. So I may have found a previous value. So I want to compare that to this new answer that I found. And that is the previous amount that we found. So I minus coin plus that one coin that we are adding in. So we're going to do this for every element in the array. Then at the end, what we're going to do is if we have actually found a valid value, if it's not float infinity, this means that we found a combination that we can use. So we're going to return that. Otherwise, we return -1, which signifies that we have not found any actual configuration in order to make that amount. So let's submit this and make sure that it works. And it does work. So hopefully this was helpful. If you liked the video, please like and subscribe, and thank you for watching.